Right now, you are falling. You don't feel it. You never will. But you and everything around you is being pulled through space at speeds you cannot comprehend, toward objects so strange that physics itself starts to break down near them. This is happening constantly, all over the universe. And somewhere out there, one of these objects is waiting. If you fell into it, something would happen to your body that sounds impossible. But it isn't. It's just physics. Stranger than fiction and far more real. You're talking about a black hole. For most of human history, people looked up and saw stars. Steady points of light, reliable, unchanging. Nobody imagined that hidden among them were places where light itself gets trapped, where time slows to a crawl, where the rules you rely on every single day simply stop applying. A black hole isn't a hole in the normal sense. It's not empty space, it's the opposite. It's matter crushed down into something almost unimaginably dense, with gravity so strong that nothing, not even light, can escape once it crosses a certain point. That point has a name. Scientists call it the event horizon. Think of it like a waterfall. Upstream, you can paddle against the current and get away, but once you go over the edge, there's no more paddling, there's no more choice. The event horizon works the same way. Cross it, and even if you had the fastest engine in the universe, you could not turn around. You could not send a signal home. You would simply be gone, from the point of view of everyone left behind. But what would it actually feel like? This is where things get strange. Imagine you're falling feet first toward a black hole, drifting slowly through space. At first you'd notice almost nothing. No air rushing past, no sense of speed. Space is silent and empty. And free fall feels like floating, not falling. You might check your instruments and see numbers climbing, gravity increasing. But your body wouldn't feel a thing yet. Not because nothing is happening. Because everything is happening evenly, to every atom in you at once. Then the difference begins. Gravity doesn't just pull you toward the black hole. It pulls harder on the parts of you that are closer to it than the parts that are farther away. Your feet, if you're falling feet first, are closer to the black hole than your head. That tiny difference in distance means a tiny difference in gravitational pull. Near an ordinary object like Earth, that difference is too small to notice. Near a black hole, especially a small one, that difference becomes enormous. Your feet get pulled far more strongly than your head. Your body starts to stretch. Physicists have a nickname for this, and it's not subtle. They call it spaghettification. You would be stretched, longer and thinner, like dough pulled between two hands, while at the same time being compressed from the sides. Eventually, you would be pulled apart entirely, atom by atom, before you ever reached the center. This wouldn't happen the same way near every black hole, though. Here's the twist nobody expects. The bigger the black hole, the gentler the approach. A small black hole only a few times the mass of the sun would spaghettify you long before you crossed the event horizon. The tidal forces near it are brutal and immediate, but a supermassive black hole, the kind found at the center of galaxies like our own Milky Way, is so large that its event horizon is far from its crushing center. You could, in theory, cross the event horizon of a supermassive black hole and feel almost nothing unusual in that moment. No pain, no stretching. Just the quiet realization, if you even had one, that you were now permanently cut off from the rest of the universe. That's the part that unsettles physicists the most. You wouldn't necessarily know the exact moment you passed the point of no return. Meanwhile, something else would be happening. Something that splits your story into two completely different versions depending on who's telling it. From your own perspective, falling in time would feel normal. Your watch would tick steadily. You'd fall and eventually reach the center in a finite amount of time, however short or long that might be. But from the perspective of someone watching you from far away, safely outside the black hole's grip, your story would look nothing like that. This comes down to one of the strangest confirmed facts in physics. Gravity slows down time. Albert Einstein predicted this over a century ago, and it has been tested and confirmed again and again, including with atomic clocks on airplanes and satellites orbiting Earth right now. The stronger the gravity, the slower time moves relative to someone farther away. Near a black hole, this effect becomes extreme. To your friend watching from a distance, you would appear to fall slower and slower as you approach the event horizon. Your movements would stretch out. Your light would shift, becoming redder and dimmer, a phenomenon called gravitational redshift. From their point of view, you would seem to freeze, forever approaching the edge but never quite crossing it, fading slowly into darkness like a photograph left out in the sun. They would never actually see you go in. Not because you didn't, because the light carrying that information would take longer and longer to reach them until it effectively never arrives at all. Two people, one event, two completely different timelines. That's not a glitch. That's just what gravity does to time. For decades, black holes lived mostly in equations. Carl Schwarzschild worked out the mathematics describing them in 1916, barely a year after Einstein published general relativity, while serving on the German front during World War I. For a long time, many physicists, including Einstein himself, doubted these bizarre objects could actually exist in nature. They seemed too strange, too extreme. That changed as evidence piled up. Astronomers found stars orbiting something invisible and impossibly massive at the center of our galaxy, tracking their motion for years and calculating that only a black hole could explain what they saw. Then, in 2019, an international team of scientists working on the Event Horizon Telescope project did something that had never been done before. They captured an actual image of a black hole's shadow, using a network of radio telescopes spanning the entire planet, effectively turning Earth itself into one giant lens. What they released wasn't a photograph in the traditional sense. It was a glowing ring of light bent around an absolute darkness at its center. The closest thing humanity has ever seen to the edge of the unknown. Physicist Kip Thorne, who spent much of his career studying the exotic physics of black holes and later consulted on films trying to visualize them accurately, has pointed out that nothing in science fiction quite matches what the real mathematics predicts. The universe once again turns out to be stranger than anything imagined for entertainment. So why does any of this matter to you, sitting here nowhere near a black hole, feet firmly on the ground? Because black holes reveal something uncomfortable about how differently reality can look depending on where you're standing. You experience your own life moving at a steady, normal pace. Every day feels like a day. Every year feels roughly the same length as the one before it. But someone watching from a different vantage point, a different stage of life, a different set of circumstances might see your same moment stretched, compressed, or fading in ways you can't perceive from the inside. Time isn't the fixed, universal thing it feels like. It bends depending on your position relative to forces you can't always see. There's something else, too. From your point of view, falling toward the black hole, the ending comes. It happens. It's real, even if brutal and strange. But from the outside, it never quite finishes. You fade instead of vanish. Some physicists argue this means information about you technically might never truly be lost, frozen in some sense at the edge forever, a problem that remains one of the most debated puzzles in modern physics. Maybe that's the strangest mirror of all. Endings can look completely different depending on who's watching. To you, they might feel sudden and complete. To someone else watching from far enough away, they might look like something that simply fades, slowly, quietly, without ever fully disappearing from view. Right now, you're not falling into anything. You're just here, gravity holding you gently to the ground, time ticking forward at the pace you've always known. But somewhere out there, it's happening anyway.